Okay, so previous video, what we're doing is we're saying if the eigenvalue is repeated, let's say just one, so we have two of the same eigenvalues, then all you do is you differentiate this guy, and that gives you your second equation. So, for example, suppose we have the matrix 0, 1, negative 9, 6. So the matrix exponential is going to, because it's a 2 by 2, then we stop it at what? 1 less than 2. So we have two unknowns, alpha naught, alpha 1. Just go ahead and expand out and then combine. You guys see this okay? So what this is saying is that our matrix exponential is going to be that guy at 2 by 2, where we don't know what the alpha naught and the alpha 1 is. That's where so we have to have two equations in those two unknowns. We form, this is not the characteristic polynomial, okay? So we're forming with the, whatever the eigenvalues are, actually lambda t. And it turns out that the eigenvalues for the original matrix are repeated. So what we have to do is we have to also differentiate this guy with respect to lambda. And so it turns out that you have the eigenvalues which are repeated are 3. So lambda 1 equals 3, lambda 2 is equal to 2. And you could check that using Mathematica. That's not a big deal. So here are our two equations in two unknowns. So this tells me immediately that alpha 1 is going to be this guy, so I can substitute that, and I can figure out what my alpha naught is. So that means that alpha naught is equal to this, so we now know. So if I put the alpha naught and the alpha 1 back up into here, here is my matrix exponential. Very nice. Okay, so going back to this guy, let me stop, the dog is barking. Sorry about that. My daughter and wife are working here at home, and and what happened is my daughter, there was a dog barking on her TV. Our dog heard that, starts barking, and then it got amplified because my wife's working online too with a video conference, and so there's all this echo of dog barking. Anyway, so that was 10 minutes of trying to quiet him down. So let's go back to 1191, and yeah, from the previous notes we found the matrix exponential for those two guys. So one was what? Distinct eigenvalues. Sorry about that. My thing's going off. And we had one with repeated eigenvalues. So, is there a way to have Mathematica do this? The answer is yes. You put in your matrix and you go matrix exponential. Boom. Simplify, and there you can avoid all those calculations. Now for your homework assignment, however, I'm going to want you to do it both ways. I'm going to want you to go through the calculation. You don't have to do it by hand, obviously, but you're going to have to set up the systems of equations, etc. Go through that just so you understand what the mechanics is, and then you could check with the one command. Okay, the next thing we're going to talk about now is the relationship between higher order differential equations. So, for example, suppose I tell you that I have a second order differential equation. Second derivative is 2 times the first derivative. A equals e to the t. And the user has specified the initial conditions. Notice you have the function x, the derivative, and the second derivative. If I think of this as position, velocity, and acceleration, I need two initial conditions. So this would be what my initial position is. This would be my initial velocity, okay? So we have to have, because it's a second order, we have to have two initial conditions, or possibly boundary conditions if we have. So what we're going to do is we're going to rewrite this single equation as a matrix equation. That's why we're messing around with that. So the trick is the following. I'm going to rewrite, instead of calling it x, I'm going to call it u, just for a moment. And I'm going to call du by dt, which is dx by dt, I'm going to call that a new variable v. So in other words, I'm going to try to take this second order ordinary differential equation and write it as two first order differential equations. Then we can use the stuff that we just did. So then when I take dv by dt, that's the second derivative, which means I can go back up to here and solve this for the second derivative. And if I do that, so if I solve this for the second derivative, then this is going to become this, but then I'm going to make substitutions, and we end up with, excuse me, why do I have this in here? Oh, get this. So then what happens is we've got the differential equations for the second order, and we have the first for the du by dt. So I can rewrite this in a matrix form. So in other words, instead of having a second order, I have two first order differential equations. And so we can write that. Now we also, excuse me, we also have to change the initial conditions. So we had x at 0 and we had dx by d0. So in other words, that's going to transform that u of 0 becomes 1. And we had the derivative of x at t equals 0 is -4, but v was dx by dt. So we have these conditions, initial conditions. Suppose we have a third order differential equation. So ignoring the, you're going to need three conditions. You're going to have to tell me what x is at 0, what dx at 0, and the second derivative is at 0. We're not going to worry about that. So we do the same thing, except we're going to have three variables. Now we're going to have u, we're going to have v, and we're going to have the w, which is, we're going to let the second derivative. So then I'm going to have a third derivative, which means I'm going to have to differentiate this again. So we're going to change from a single third order to a single system of three unknowns. So if I solve for the third derivative, that's going to give me the dw equation, and I can put all that together here. So I'm going to solve for each of the first order new variables, and then just rearrange this in terms of u's and v's and w's. And notice we're back to the same type of thing. The derivative, first order derivative, a 3 by 1. Here's our constant matrix A, and so we can go through all that e to the at stuff. And what we're going to do next here is talk about canonical forms. So just as we talked about in when we were talking about bifurcations, is we looked at specific types of differential equations. These were nonlinear; they had squares and stuff. But it turns out that we're going to be looking at first-order systems like this, which are going to be approximations, linear approximations of nonlinear things, and we'll pick it up there.